Welcome to today's webinar on design of footing and anchoring. We are using GoToWebinar, so just a quick introduction. You should see a panel on the right which will help you to define the audio settings and enter questions to the field so we can get over them. You are by default all in muted mode, so use the chat or raise a hand to get attention. Allow me to introduce myself and the team. My name is Juraj, and we also have our two product engineers, Martin and Adam. We will be going through 4 examples we put together, and through all the questions you have. We will do that continuously during the webinar and also after the examples at the end. We are a team of people who've been developing software for structural engineers for quite some while, especially as some of our development guys have a lot of experience. And Idea Statica is dedicated to details. We do not develop software for the modeling of the structure as a whole, like SAP 2000, Start Pro, CI Engineer. We focus on details, joints, cross sections, beams, and provide code checks for that. We work a lot with universities to verify the results, and we link Idea Statica with various programs to ensure BIM workflow. And really it's about making the project safe, code compliant, and fun to use, easy to use to get the job done. And you all have a tool today that you use for structural analysis and design. We will demonstrate how we work with it, because the software, it's a good tool. The thing is that majority of these programs, they focus on the model as such, but the majority of defects, if they happen in a structure, are related really to details, and that leads to waste of time or material. So that's why we in Idea Statica focus on joints and connections today, footing, anchoring. Without further ado, let's jump into the first example. I will give presenter to my colleague Martin, and let's do that.
Good afternoon. So as a first example, I will show you how to model a connection. It will be a footing with a diagonal. So let's start our Idea Statica and module application Idea Statica Connection, and let's create a new project. As you see, I will use this wizard which can help me to model my project. So I will select the option anchoring with topology, with a column, with this diagonal, and let's wait for the generation of the project. Now we can see that some column and a diagonal was prepared, and also the footing or base plate as well. Now I will add a new member. So let's use this button, add a new entity, and in my case I will use cross section, and I will change it to HEB 200, and I will modify the position of this member. So as you see, I have a possibility to put any member to really general position, so I can play with the slope, rotation as well. And just to finish this input, I will change the length just to have a more space for modeling of my connection. Now I will continue with modification of this of the column. So let's select it. First of all, I will again change the cross section. So let's use HEB 300, and I will shift it by the offset X to -200, and as you see, that helps me to model the gap between the beam and the concrete block. Again, I will a little bit change the default length to 800 millimeters, and that's the input of the column. Finally, let's change the cross section of the diagonal. In my case, I will change it to key 8084. Okay, and again, let's a little bit extend it. So now we have prepared the all members which we are going to connect and checked. The next step which I will do now is the definition of the load. So here I will define the internal forces on all members. So let's start with a column. Here we put the minus 350 kilonewtons. As you see, we can immediately check this force in the 3D view. The same input I will do for the diagonal, minus 50, and finally for a beam, 10 kilonewtons as a normal force, shear force minus 80, and the bending moment 150. As you see in this table, I have the possibility to define all six types, let's say, of internal forces. In our case, I will just use this setting, and I will use the loading in one plane. So that's the definition of the load. Now I will define the connections. First of all, we see that already the manufacturing operation base plate was added automatically by the wizard, because I use this option of the anchoring. So now I just need to a little bit modify some properties of it. First of all, I will change the thickness of the base plate, the size by the offsets. Yes. Now let's change the type or define the anchors. In our case, I will use the M24, and the length should be 400 millimeters. As you see, we have some options just to define the straight anchor or the washer plate, circular or rectangular. I will use this rectangular option, and let's keep the size of that, but I will change just the position of the anchors by the offsets or by the post definition of the layers of that. So that's it. Let's continue with the welds. I will define the size of the weld at 6 millimeters. Let's keep the double fillet weld, and finally I will modify some properties of the foundation block. First of all, let's change the offset, the size, let's say, of this block, and the depth to 800 millimeters. I would also like to mention the option, by definition, the way of the transferring of the shear force. We can use the friction, shear iron, let me show it, or we can check the anchors for the shear. In our example, we will use this option of friction. We can also define the mortar join if necessary, by some thickness of that. So that's also possible. Now I will deactivate this option. Okay, so that's it. Next operation will be the base plate, the end plate. This I will use for the connecting of the member M3. So let's define the member M3 and let's connect it to a column. Now I will change the definition of the dimensions from symmetrical just to profile, because that enables me to define the offset in all directions separately. So that helps me to, because I will use this part of the end plate for connecting of the diagonal. Yeah, so I will a little bit extend it to the top, and I will also define some offsets in all directions to have, for example, here's this enough space for this double fillet weld. Again, let's change the size of the bolt and arrange the position of them. So I will add some another rows to the top, and I will move this bottom bolt a little bit up because it's in collision with the weld. Okay, so that's it. And finally, again, I will change the welds to 6, the size of weld to 6, and I will keep double fillet one. Okay, so that's the connection of the member M3. Now let's connect the diagonal. For that I will use the operation connecting plate. Okay, so let's select the diagonal. We will define a new plate. In some cases I can, for example, use an existing one. And we need to connect it to a member M3 and also to a plate EP1, that's the end plate. As you see, a new connecting plate was automatically added. Again, I would just need to change the properties of that to put it into the correct shape, and I will move the position of the connection a little bit along the member axis, and let's add, for example, another bolt here. So for that I can add a new row of the bolt and change the size of that. As you see, I have some possibilities to, for example, select the type of this connection. For example, I can use the notched member, or I can use the notched plate, or cap plate. So I will keep this option of the cap plate, and just to set the correct size again of the welds and the type of them. So as you see, I will use the double fillet weld for the tongue and the one side fillet weld for the connecting of this tube, because of course the welding inside the tube doesn't make sense in this example. Okay, so that's it. Now, of course, I expect that you can see this collision of this connecting plate and the cap plate. We can fix it by editing of the shape of the connecting plate. For that, I will use this editor, and I will select the gusset, and I can define a chamfer on that. So we need to put it on the corner number 2, and the size is 70. So now we have, as you see, we fix it, and it's now it's okay. So that's it. And the last operation in this example will be the stiffeners. So I will add stiffeners on a column. Now you see that we have a default value in a 0 position. I will use this option by alignment to an existing member. In this case, I don't need to define the position by numbers, but it's automatically put it into the position of the flanges of the member M3, and I will just change the thickness, type of the welds, and the size of them. Okay, so that's it. Now we have defined our connection, and we can continue with the check. For that, I will use this item in the navigator and I will start the calculation. Now, as you see, the nonlinear analysis is running. We need some set of the iterations to calculate the results, and let's wait for them. Okay, and we will see, and we will check the status of this. So as you see now, we have some, for example, some troubles with some plates. We would need to check it, and also some anchors are in orange. This quite nice overall check can give us real nice view of the status of all items, and we can go through them. First of all, I would mention the plates. So for example, we can really identify some critical plates and some parts which doesn't satisfy the check. So for example, if I select this connecting plate, I can use this overall check or also the strain check, and we can see some parts of where the plastification is really too high. If I use this plastic strain, I can really see immediately the parts which are too critical for this. For example, if I activate the mesh and the deformed shape, I can really see where I have some troubles. So in our case, we see that we have, for example, a really weak the end plate, so we can check it. And if I go back to the design and select this plate directly, I see that I have thickness only 10 millimeters, and if I change it to 16, I can enlarge this this plate and recalculate it again. Okay, so now as you see, now my connect or joint is now okay and satisfy all checks. If we go back to this view, we can go through all available checks. So for example, if we continue by bolts, we can use this table of bolts. I can really immediately select any bolt in the connection, and it's automatically highlighted here in this table. I can see for example, the tension force in the bolt, shear force, of course the unity checks, shear check and interaction check according to the raw code. As well, the same is for the anchors. So again, we can see all checks of the anchors, the tension force, and also the related concrete breakdown resistance, for example, according to the attack, and we see that it satisfy our check in this case. We can continue by welds. The same. If I select any weld in the project, it's automatically highlighted here. If we, for example, would like to know the most used weld, I can sort it by the column of the check, and I can see that, for example, I have the most used weld is this one, this connection of this connecting plate. Yeah, so we can see that it's this weld of the connection. Then I would like to show you the check of the concrete. So in our case, because today's webinar is about the anchoring, we can provide you also the check of the concrete block, because we can calculate the stress and the contact between the concrete and the base plate. Yeah, so here we can see the results coming from the fine element analysis, and we can also provide you the check of this concrete block and the check of the according to the Eurocode and calculation of the contact zone. Yeah. And the last available check in this example is the shear. As you remember, I have used the option deflection for the transfer of the shear force between the base plate and the concrete block. So here we can see the maximum shear force in the base plate and the corresponding design shear resistance, which is calculated for according to the friction. Finally, I would like to show you, for example, the view with the bolts and the deformed view. And maybe let's enlarge it a little bit more. So in this view, we can see immediately our behavior of this connection. I think that you can really see some deformation of the base plate, the tension force in the anchors, the plastification of the connecting plate, the deformation of the diagonal which is coming by one side connection. Yeah, so there is an eccentricity, and here I would maybe just to show you the forces in the bolts. So let's maybe go back to the overall check, and if I select this bolt or this one which is connecting of this diagonal, we can see that there is a tension force in the bolts, yeah, and this force is coming from this one side, and connection and the eccentricity of this bolts. Okay, so that's it. That are the results. Finally, let me show you the output protocol. We can provide you one line protocol, which is very brief, or one page, which contains some picture and some basic information, and as well the detailed. For the detailed one, you can see that you can manage the content of that. We can, for example, add a bill of material, theoretical background, some more pictures if necessary, and let me regenerate it and go through that. So you can see that we have this view of the connection, summary of the load effects which we defined, the brief overview of all checks, and in detail all tables which are already demonstrated. Yeah, so here are the tables of checks for the plates, anchors, bolts, the welds, and here we have this bill of material with some detailed drawing of all plates defined in our example, and finally the theoretical background which contains the description of the CBFEM method, which is in background of our analysis. So that was the first example. Now I would like to continue with the demonstration of the link with application Tekla structures. We have full and easy integration into the Tekla structures. As you see here, I have available item idea connection directly in the menu of the Tekla, and I can export a defined connection from that directly into our idea Statica connection. For that, I just need to start or click the icon and start the export. Now I select a node, members, which I would like to export, and finally the entities of the connection, so plates, welds, and bolts. Now I can define the path and the name of the project. So let's keep it the default setting, and now just let's wait a while for the generation of that. Now a new project of idea Statica connection was generated. Yeah, just as you see, we have the same view. Maybe let's go here to show you that we have received the same topology of this connection in our idea Statica connection, and as you saw, it took only a few seconds to do it. This link can save us a lot of time because as you see, I have received all members, all bolts, welds and plates, and now I just need to define the load, which was not defined in the Tekla structures. So for that I can create a new set of the load, and I will put some, just to demonstrate some forces on that. So let's put here just the normal forces, and we can calculate it. So let's go to the check, and I will start the analysis, and we can immediately check the connection defined in the Tekla structures. Yeah. The results are of course the same, so I will just briefly show you, for example, the strain checked and the deformed shape. Again, here we can see nice deformation of connecting plates coming from the eccentricity of the connection of diagonals. Maybe we can just see the stresses in the plates as well. And I think that's all what I wanted to show you in this example. Now let's continue with another one, with another project. For that I will create a new project, and I will model a tie. So it can be, for example, some connection, modeling of a tie to a concrete member, concrete beam. So again, I will create a new project. Type will be again the anchoring, and in this case I will use this just the column, and I will change the cross section. So first of all, let's select the SHS 8085, okay, and I will a little bit extend it, and I will change the slope, yeah, because as I wanted to model the tie, so we can put it into, we can change the direction of the member, and I will also change the type of the member because I would like to connect it by just one bolt. So I will explain a little bit later. So that's it, and we can continue with the load. So let's define some force on that. I can use just the 10 kilonewtons as a normal force here, and I will modify the properties of this base plate, which was already added. So let's keep it on a column, of course, but I will change the thickness of the plate and the size of that. Yeah. So let's set it like this, and I will change the position of the anchors to have just 2 anchors in the center of the plate, and finally I will disconnect the member from the base plate so I can deactivate the welds, and because I would like to connect it by the L profiles, and I will change the depth of the beam. Okay, so now we have some concrete block which represents the concrete beam with the connected base plate, and now let's connect this member to that by the L profiles. So to that I will edit operation cleat, and I would like to use it on a column and connect it to a member, oh sorry, the plate base plate BP1, and I just need to set the correct profile. So let's use L90 and 60 to 6. Okay, so we have it. Just put it into the correct position, and I will set as a welded. And let's deactivate the welds to a member. Okay, and set the correct size, in our case 3 millimeters. So that's the 1L profile. To define the second one, I can use the option copy. So let's copy that, and I will just select the member part web 3. Okay, so now we have the L profile on the other or second side. And finally, let's define a bolt to connect all this, to connect the members to L profile. So for that I will use the operation bolt grid. We need four items, and we need to connect the member grid 1, and I need to select the correct the parts of the member. To that it can help me that I can just put a mouse into the correct position, and then you see here in the bottom I can see the tooltip of the name of the part which I need to define. So we need to define a web 1, and the second member will be again the member, but the column and web 1. Now we need to put a column and a web 3. We can check it from the opposite side. It's a web 3. And finally, let's put member grid 2, and it's a web 1. Now I will put a bolt into correct position, and I will a little bit shift it down. Okay. As you see, I forgot to enlarge the grid. So if I go back to the grid, I will set the width of that, or length, to 70 millimeters, because I would like to have it a bigger, and also for this grid. Yes, and now we have the bolt in the middle of these plates, as you see. So that's definition of that, and let's check it. So I will start the analysis again, and we can see all available results again. So we can, for example, check the deformed shape with both forces or tangent bolt forces directly in one picture, for example stress concrete or plastic strain. So we can really identify the critical part of our project. If I go through the results again, we can check the all plates. Maybe we can check the shear block again. So if we see the stresses in concrete, we can see the peaks in the contact which are coming from the praying of the anchors. We can check the anchors and tangent forces in the anchors as well, and that's it. I think the rest is the same as in the previous example, so we can skip this part of the demonstration. The last example for today's webinar is the link with the Autodesk Workbox structural analysis. So in this program I have, for example, this steel construction, and as you see we have implemented an add-in into the robot which can help me, or it can enable me to export of selected members. So if I start this add-in, then a wizard of Idea Statica is started that can help me to create a new project with selected members. So let's wait for this a second. Yeah, now we see that we have imported all members with profiles and as well the forces. I can merge the column members because it was defined as a separate members in the robot, and I would like to model it as a continuous beam. I will set it as a bearing. If I go to a next tab in the wizard, I can see all imported load cases and as well the all imported combinations. As you see, there is a big number of combinations which were defined in the robot. Just to speed up our demonstration, I will delete them and I will just select keep one of them. So let's delete this combinations. I will keep just the one. As you see, I can really select which combination I would like to check, and I can play with the coefficients and as well. And finally, let's generate the project. So if I click the finish, now again the Idea Statica project is generating, and we can see that a new project was created from the definition in the robot. Here I can use, I can just need to, or sorry, you see that I received all members as well all internal forces. So I don't need to take care about input of the internal forces and the geometry. I will just a little bit extend the imported members, these diagonals, to have enough space for the modeling of the connections. Okay, and DM2. And we can go immediately to a design. Now, again, I could model the connection of all members, or I can use some template. So I have prepared a template in advance. So let's just select a member size, and as here you can see this template. So if you have, for example, the member with the connection with the same topology, you can define your own template and use it repeatedly for some another connection. Now what I need to do now is just to set a correct L profile for the cleat. So let's put it, for example, L110, and now the member is connected by the cleat. So as you see, I have received again a very fast input of a connection to check, and we can start the analysis. Yeah, and we have the check of that. You can see that in this case there is a quite low use of, for example, of the bolts. So we can check again the forces in the bolts, the check of them, the welds as well. It's the same for all members and the connections. So that's all what I wanted to demonstrate today. So now we can go through your questions, and I will ask my colleague Juraj to check the questions you send us.
Very well. We have a couple of questions here. The first topic is the anchors. So we got how to check anchors in reinforced concrete, and another question related to that. It is similar if we check failures of the anchors or model the breakout cone of the concrete.
Okay, so the check of the anchors, and can go back to the first example. For example, you can see that if in this first example, if I go back to the design, we can provide you the check of the anchors according to the attack, and we this code provides the check of the not reinforced concrete. Yeah, so this is the setting of the code. On the other hand, we can provide you the option to deactivate this concrete cone breakout resistance, which is calculated according to the code. So if I deactivate it and start the analysis again, then only the check of the anchors according to the standard steel code is done, or in fact there is just the forces and the check of the tension of the anchor, but there is no check of the concrete cone breakout resistance. Yeah, so in this case you can see that we can provide the real forces in the anchors, and you can, for example, use it for the detailed analysis, or you can use in the application from Hilti, which can provide you also another option of the check of the anchors. So I think that's it.
Very well. Another question is about can we use and define preloaded bolts?
Mm-hmm. Yes, so yes, this is available. So for each group or definition of the bolt, we can define the type of the transferring of the shear force. So if I, for example, select the end plate in our operation, and you can see this option shear force transfer, and if I change this value from the default to friction, then we can calculate the preloaded bolt, and we can check the friction between the base plate and the flange of the column, and we can provide you the check of this preloaded bolts. Yeah, so here we have now the new table of the preloaded bolts with calculated forces, check of these bolts according to the Eurocode. And you can see that there is a different values of the checks, because we can check it for the friction, and there is now, I would expect, a smaller deformation in the base plate coming from the shear. And so another question.
Here we have a question: how can we get a trial of Idea Statica? Let me take the presenter. All right. So to get a 14-day trial of Idea Statica, kindly either visit our website and fill in the form, or there will be a survey after the webinar. You can just indicate that we should send one to you. We will also send a recording of this next week, and we're looking forward to all your questions. The easiest way is to use our website, ideastatica.com, to either get a free trial, or if you want to ask anything, just fill in the form, and we immediately get onto it. All right. Let me check more questions we get in the meantime. Right, so the first is, the bolts or anchor resistance are defined by stiffness relation. If yes, is this coefficient accessible or possible to be seen and modified also?
Okay, yeah, so we can set, for example, some parts of the code, and the code settings, that's one part, and I'm not sure. Maybe now, if you are asking about the, let's say, the working diagram of the bolts and the anchors, this is you can just select the grade of the steel now. What we are improving is that in the version 8.1, we would like to implement the possibility to define user's grade of the anchors. Yeah, so this will be available in the next version.
Very well. The next question is, if the shear is transferred by the anchor, why the shear resistance is not calculated according to the Eurocode, the EN 1993-18?
This is provided, yeah, so we can, if you activate the option that the shear is transferred by the anchor, then we check, let's say, both checks, and the worst is used for the or is used as a critical one. Yeah.
Very well. Next question is about Tekla link. When we import from Tekla structures, plates are positioned with local coordinates, which are quite complicated to modify and see sometimes. What is the easiest way to modify joints when doing this?
In this case, I would recommend you to update your model directly in Tekla. And you can, as a new feature coming in the version 8, you can update existing project. So if you, for example, define some load in your project, you can update by the link existing project. The operations, or for example, the position of the welds would be updated, and you will not lost the definition of for example, of the load cases. Or you can import the load cases through the Excel sheet. That's as well possible, and that can speed up your process. But definitely, I think that the best way is to keep just one point or one model, and in this case, it's the Tekla structure model. Yeah, to keep the synchronization between both projects.
Thank you, Martin. Is it possible to create opening holes in hollow sections? Next question.
This is possible in the case of the rectangular tubes. It's not possible for the circular tubes, but you can define it in the rectangular tubes. Yeah, maybe I can show it if I take a presenter. I will make me a presenter. Okay, if I will go back to, maybe we can try to do it here. And if I go to the design, I can add, as you see, I can define opening. And if I select member D, position, I think, if I select some correct, it's too far. Oh, it's still too far. And okay. And I just need to select the correct web. It was web 2. Maybe let's put it into web 4. Web 4. Yeah. And as you see, I edit this opening. I can change the size, for example, to 30, and the position to have, to have it here. And we can define this opening into any member. Okay. And for I have change. I have rectangle, circle, and so on. Another question?
Yes, we had the question, what are the standards covered?
Okay, so we can provide you the checks according to the Eurocode and the AISC, that's the American code. And you can select it, maybe just to show me again. If you defining a new project, I will create a new project. You can select which code should be used for the for your new project. So here you can select or pick up the Euro code or the AISC.
Very well. We've gone through the through all the questions. Before we wrap it up, let me show you the resource center at our website. When you go to resources, Idea Statica Steel, we have a tree of documents, of which the most easy to use are the tutorials, just step-by-step video, and always the source files to try it out. Then if you want to dig into the verification and validation, we have verification studies according to AISC and Eurocode, so some of the articles. We have the theoretical background explaining the method and the calculations in more details. We have case studies from our customers, all the videos, and also gallery of projects for joints to play with right away. This is all online, accessible from our website, as well as to get the free trial. Thank you all for coming. Thank you for the questions, and feel free to get back to us after the webinar. And one last question popped in, how to model a slotted hole in Idea Statica Connection.
This feature is planned for the version 8.1. So now it's not possible, and we are going to implement it into the version 8.1.
Which is October of this year. That's a frequent question from our customers, so we put it into the development plan. Will be done October 2017. All right. Thank you very much, and have a nice day. Bye-bye.
Bye-bye.